What is up, Calc kids? We are here in section 4.5 learning about linearization. Ooh hoo hoo. It is a really, really cool tool. It is it may not be the most practical thing, but it is a really cool usage of derivatives and like all of this like slope at a point and like tangent line stuff really kind of like comes to fruition with this like applicable like technique that we're about to talk about. And what's really cool about linearization is that it's like the details of it are actually within the word, right? You see the word linear in it. So yes, we are dealing with lines, but we're dealing with the idea of being locally linear and seeing how that can help us to approximate some values, right? So that's kind of what linearization is. It's basically using tangent lines to kind of approximate values. Okay, and I'm gonna show you some graphs and stuff, and hopefully it'll clear up like what exactly we're doing here, right? So let me just start off with just asking you a question, right? If I asked you, what is the cube root of I don't know, 8? Well, hopefully, you don't have to pause the video, and you can answer this quickly, and you can tell me that it's 2, right? And yay! Wow, that was so easy. Wow, Mr. Lee, linearization is so easy. Well, that's not linearization. What if I kind of tweaked the value? What if I kind of tweaked the what we did instead of cube rooting something that we know? What if like I asked you, what's the cube root of like 7? Well, that's a little harder to answer right off the top of your head, right? It's not, you're not really sure. You know it has to be less than 2, right? Because, cube root of 8 is greater than cube root of 7, okay? And you do know it has to be like cube root of 7 is also what is it? Greater than what's the I guess 1, right? So like the answer has to live somewhere in between 1 and 2, but sometimes we don't want that as an answer. Sometimes it's not good enough as an answer. Maybe we want something that's closer to this, right? This is where linearization kind of comes into play. We are going to find the slope of the tangent line. I'm sorry, no, the equation of the tangent line at 8 for our function. Wait, we have a function here? Yeah, we've been playing with the function, and here it is. It's right here. It's the cube root function, right? If you think about it, I can define a function as cube root of x, and I know that when my input is 8, my output should be 2, right? Well, if I want to figure out a really, really close value to what 7 is going to equal, well, I can kind of let me kind of draw a picture. I think the graph really explains linearization really well, right? If I sketched the cube root of x, right? You guys know that this one's the one that kind of looks like this, right? It's a really crude drawing, I know. But just imagine that this is 8 and this height is 2. All right, so we're at 8 comma 2, and we want to figure out a nearby point. We want to figure out, well, what is this going to be? What is f of 7 going to be? Oops. What is f of 7 going to be, right? What we're going to do, which is a lot faster and easier, is we can find, let me just zoom in here, we can use this idea of local linearity and find the slope of the tangent, I'm sorry, the equation of the tangent line at 8. You guys should be like masters at this by now. I feel like I've asked you guys to do this like a gazillion times, right? And what we're going to do is find this equation of the tangent line at x equals 8, which you guys know how to do. And then with said line, right? With said line, I'm gonna call this my L of x function, right? L to like represent like the linearization or the line or the locally whatever line L whatever, right? I'm gonna use this, and I'm going to approximate with my line. Now, that's going to give me this point right here. I can't really zoom in anymore, unfortunately. But is this green point, is this equal to f of 7? No. But it's really darn close. And that's the point of linearization. It helps us to approximate at certain values. Now, Mr. Lee, can't I just type this into a calculator and just, get an answer? Yeah, of course you can, silly, right? Yes, you can punch 7 into the cube root function and do it that way. But sometimes in math, okay, a lot of times in math, there are functions out there where you can't, where you simply cannot do it either because the technology doesn't exist yet or for whatever reason. So we need these approximating techniques to help us get really close to the answer. Now, if you're curious, if you are curious, actually, you know what? No, we're just going to do it. We're just going to do this problem. So what did I say we needed? We needed the derivative at 8, right? Because we need L of x, which is the slope. I'm sorry, I keep doing that. The equation, I wrote it already. The equation of the tangent line at, let me make a note here, the point that we know. This is the known point. Okay? The red one is the one we don't know. All right, I hope that clears that up. So we're going to make a tangent line equation at the point that we know. Well, luckily for us, we have the point, and the other thing you need is the derivative at that point, right? So let's figure that out. Well, what is the derivative function here? Well, this is x to the 1/3, and then this becomes 1/3 x to the negative 2/3. Okay, and then we plug in 8 into here because that's how we get this guy. So if I plug 8 into there, let's see, what do we get? We get 1/3 times 1/8 cube root squared. And that is equal to, what is that? That's 2 squared, so that's 4. So it's 1/12? I hope that's right. I think that's right? Cube root of 8 is 2, and 2 squared is 4, and 4 times 3 is 12. Yeah, okay. So equation of the tangent line, or I'm going to use the new variable, or the new definition, L of x, right? This is the equation of the tangent line at the point at the known point. Okay, once again, this is the known. This is the known point because we know what the cube root of 8 is, right? And this equals, well, how do we do the slope of the equation of a tangent line? It's y minus y1 equals the slope. Oopsies, it should be 1/12. The slope times x minus 8. All right, and if I can kind of go back to the picture, this equation is this guy right here, that green line. All right? I hope that makes sense so far. Now, the whole point of this, the pièce de résistance, this green line is going to represent what we want, this approximation for 7. So let's see it. What happens when I plug 7 into my linearization line, my line that's approximating this? So y minus 2 equals 1/12 times negative 1. And then we get y is equal to negative 1/12 plus 2, which is, what is that, 24/12, and then 24 minus 1, that's 23/12. And this is our approximation for f of 7. Don't believe me? Let's see here. I'm going to hit in the calculator, what is the cube root of 7? And then also in the calculator, since I don't know what it equals, right? It's about, like we said, it's less than 2, it's greater than 1, right? So, and let's compare our answers here, okay? Why don't you guys do this, right? Pause the video and punch into your calculator, and then be like, oh snap, I learned something. Right, so I just punched this into my calculator, cube root of 7, and it spat out 1.91293118, yada yada yada. And then right under it, I punched 23/12 into the calculator, and I got 1.91. Interesting. 6 repeating. So what just happened here? We just approximated the first 3 digits of cube root of 7 without even knowing how to do the cube root of 7. We approximated the first 3 digits by using this equation, this linearization technique, And we got pretty darn close, if I do say so myself, right? 0.004 off. That's pretty close, and it makes you think. Well, what could we have done to get a closer answer, right? Well, probably like if we were looking for f of 7.5. Yeah, I think our answer would be even closer to the actual, cube root stuff, right? So it's interesting to think, like, actual versus experimental versus, actual, and things like that. It's all this stuff comes into play, and all that stuff. So hopefully you guys have a good idea of what linearization is now, right? It's just using a tangent line to approximate some values. All right. All right, so at this point, if you're good, if this first example was good enough, then by all means, you can close the video and you can move on and try some of the practice problems I posted. If not, stick around. I will do one more example with you all, right? Just because I care about you all so, so very much. All right, let's call this example 2. All right, and I don't know. Let's look at I don't know. Let's look at one with trig. I think that's fun. So the problem goes f of x. They give you cosine of x. That's pretty easy. And then it says use. Sometimes the phrasing will all be different, but they all do the same thing. Okay, so use. No, it says, I'm sorry, it doesn't say use. It says find the linearization. I'm going to do lin for short. Find the linearization of f of x, in this case it's cosine of x, at x equals pi over 2, and use, I'm going to call it L of x, right? So let me just make that clear. So this, I'm going to say this is L of x, right? And use L of x to approximate cosine of 1.75 radians. Interesting. All right, so here we go. So what are we going to do here? So first, we are going to find the tangent line at the known point. Now, what is the known point? The known point is this guy right here, right? I know how to find cosine of pi over 2. That's one of my my unit circle values, right? So let me find my point quick here. Cosine of pi over 2, what is that? That is 0, I think. Right? Yes. So my point here is pi over 2 comma 0. So that's going to be my like x1 y1 that I'm going to plug into the tangent line. And if I'm going to approximate here, well, now I need the derivative just like before, right? I needed the derivative at the point that I know. So the derivative of cosine of x is thankfully sine of x. And we're going to need the derivative at pi over 2. And what is sine of pi over 2? Well, isn't that just 1? So the derivative at pi over 2 is going to be negative 1. Great. We have everything we need, right? We have our point. We have our slope. So let's find L of x, right? L of x is going to be y minus 0 equals the slope times x minus pi over 2. Beautiful. I like that 0. Makes the equation very simple here, right? L of x is just going to be negative x plus pi over 2. This is my approximation function. And what are we going to do here? We are going to approximate, this is what we want, cosine of 1.75. So that means I need to plug in 1.75. And I think this is the part where you can bust out the calculator, because I want to know how close am I, right? How close am I to the actual answer? So I'm just going to punch this into my calculator real quick. 1 second. All right, and I get approximately negative 0.179. And we want to know how close is this to cosine of 1.75. Well, let's see. I'm going to type in cosine of 1.75. And holy shnikes, it becomes negative 0.178. Dang, that is pretty darn close, if I do say so myself. All right, that is pretty darn close, right? So once again, this is the point of linearization. It's so that we can compute these kind of out there values without having to use the actual function. And this is actually sort of like crazy, because it's kind of hinting at what we're going to be doing later in the year with series, because that's what series are going to do. But I won't talk about that here. I don't want to scare you guys too much yet. All right, so hopefully this example helped you out. You know what? I'm feeling crazy. I'm going to do one more example. And if you guys are good with this second example, you can just stop here. If you guys want to see one more, by all means, here's another one. just for funsies. All right, here we go. Example 3. My function this time is root 1 plus x. And it says, very similar, right? We're going to use this and we're going to approximate root 1.02 without a calculator. Interesting, right? So we're going to use this function and use it to approximate the root value of root 1.02. Now, we don't know what root 1.02 is, but do we know something that's close to this? Do we know something that's close to this? And the answer is yes, we know root 1. We know that root 1 is 1. So what does my input have to be for the value to be root 1? Well, then my input would just have to be 0, right? If I do f of 0, well, we know that root 1 is 1. So there we go. Boom, we got our point. It is 0, 1. We now need our derivative at 0, right? So what is our derivative here? Well, this is the same thing as 1 plus x to the 1/2. So that's going to be 1/2 1 plus x to the negative 1/2. Ew. But we're going to plug in 0, so it's going to come out nicely, I think. So I plug in 0, I get 1/2, and the rest of it just kind of goes away. I got my point. I got my slope. Let's find the equation of this tangent line. This linearization function goes y minus 1 equals 1/2 x minus 0. Awesome. And we are going to use this to approximate 1.02. So let's plug that in and see what we get. Here we go. So we go y minus 1 is equal to 1.02 over 2. Whoops. Whoopsie. I made a mistake here. All right, so it's really, really important to keep track of your function. We are approximating 1.02, but with respect to our function here, right? And our input, this means our input is not 1.02, our input is going to be 0.02, right? Because if I plug in 0.02, that gets me root 1.02 with respect to my function, okay? So please be careful with that. If my function was root x, then yeah, that would be a different story, but it's not. So we would have to pick a different starting point and yada, yada, yada. So watch out for that, definitely, for sure. All right, so I'm not plugging in 1.02, I'm plugging in 0.02. So here we go. This becomes y minus 1 is equal to 1/2 times 0.02, which is the same thing as 2/100ths. And then that simplifies down to 1/100ths plus 1. So that is 101 over 100. We get, and that is the approximation. This is the approximation for root 1.02. Let's see here. Let's test it out. I'm going to punch this into my calculator. 101 divided by 100 is, well, oh shoot. Well, there it is, 1.01. And the actual answer of 1.02 is approximately, let's see here, root 1.02. Let's see, 1.00995. Wow, pretty darn close. Pretty clever, sis. Right? Connect 4? Never mind. All right. So there it is once again. So this is a good way to check your work, especially since you guys have calculators and stuff. If you get really close to the actual answer, that probably means you're correct. All right, so there you go. 3 examples. This is a really long video. If you thank you so much. If you have any questions, please reach out. All right. Good luck. Godspeed. Take care. I'll see you in class.